formation. It's stable over the lifetime of the universe because it's still existing, and it's feebly interacting with ordinary matter itself. So potentially it could interact via the weak force. So when we think about the Standard Model, which is such a solid picture of particle physics, well, in fact, there's no candidate in that model that could represent dark matter. So we are looking for beyond the Standard Model physics, which is new physics, exciting stuff. Now, as to then candidates, well, they can range across a wide range of masses, all the way up to the planet scale. But what I'm going to focus on today is this region, the weakly interacting massive particles. So weakly interacting massive particles, they're compelling as a thermal relic of the Big Bang that would have been frozen out during the history of the early universe. And we have what's known as the WIMP miracle, which describes the apparent coincidence of an annihilation cross-section roughly at the weak scale, being able to then produce the observed relic density of dark matter that we see today. And that then also confers that the mass range of the WIMP must be between about a GeV and 100 TeV. So how might we look for these WIMPs? Well, I mean, this is a pseudo-Feynman diagram, but it sort of represents the three kind of ways that we can attack this problem. So we can look to detect it indirectly through the products of its annihilation. So by looking again out with telescopes or looking at neutrinos actually with IceCube down in the South Pole, that could have been produced by dark matter annihilation in the universe or in our cosmos. We could look to produce dark matter through collider experiments. We'd be looking for missing momentum, and this is the only way that we can really probe dark matter that's in our galaxy. We can look to directly detect it. So some factors that come into play with direct detection, well, that recall rate is going to depend on a few factors. So one, when we think about that dark matter halo and our relative movement within it, well, that we have not only the local dark matter density of about 0.3 GeV per cubic meter, but we've also got the relative speed of the WIMP wind coming roughly from the direction of the constellation Cygnus, with a sort of average velocity of about 220 kilometers per second. So we've got this Maxwell-Boltzmann distribution in the velocities. We also have to think about the nuclear physics. So thinking about the target mass of the thing we're trying to detect the WIMPs with. Well, we're expecting the WIMPs to be well matched with the nucleus of our target. And so therein, things like nuclear form factors come into play. And then it's the particle physics aspect. Mainly here, we're kind of concerned about what that WIMP mass is and its interaction cross-section. So those are the two parameters that we typically use when we come to produce plots on limits and limits on the interactions of WIMPs. So with that scatter of a nucleus, you could excite that nucleus and you can get the production of scintillation. You can have energy loss through atomic motion or heat that we detect as phonons, or you can ionize the atom and you'd obviously then get charge. So there's several different channels that we could hope to detect. Obviously, it's more effective if one is detecting more than one of those channels. But you can see the kind of spate of different technologies that have been utilized to try and find dark matter. So we've got things like the superheated bubble chambers. So that's a picture of Pico. We can see some background bubbles forming in the refrigerant that they use. There's a picture of a calcium tungstate crystal that's being used in CREST under the scintillating bolometers. We've got the scintillators such as, liquid noble, single-phase liquid noble detectors like DEEP. We've got also ionization heat bolometers like Super CDMS with their germanium and silicon crystals. And then we've got the dual phase Noble detectors that can detect both scintillation and ionization. And that is the technology that I'm going to focus on today. So there are, of course, a lot of challenges to directly detecting WIMP, so you can't see the title there. Well, one, the local WIMP density means it's actually tantamount to having about 2 WIMPs in that coffee cup. The WIMP flux is such that even though there's 10 million per second going through your hand, with the exclusions that we already have, we know that it would take over 10 to the 4 years for there to be an interaction in that area. And the WIMP recall energies we know to be roughly about 10 to the minus 9 times the flying energy of a flying mosquito, so of the kinetic energy of a flying mosquito. So these things necessitate quite some, facts about our detector. It needs to be large in mass. It needs to have a low background rate that we have a chance to see that WIMP interaction. And it must have a low energy threshold to be able to see these kind of recall energies. So on the theme of then those dual phase detectors, specifically xenon now, you can see here the kind of history of setting limits on the scalar cross-section, interaction cross-section for a typical WIMP, and how things have progressed over the past decades. So we start out from the sort of phase of the solid state, germanium bolometers, going through sodium iodide, through various other cryogenic solid state detectors. Now we see the advent of the liquid nobles, and in particular that purple line there shows the improvements that we've seen in the limits for xenon-based detectors, which is greater than a Moore's law sort of trend over the past 15 years or so. And I will be focusing on LUX-ZEPPELIN, which I'll introduce more properly later, but here's how things have evolved. And it's really rapid progress, right? Going from just less than 20 years ago now, from a 10 kilogram region detector with Zeppelin, all the way through now to almost 10 tons. So, orders of magnitude increase in the target size. And part of the reason why we've been able to have this rapid progress is sort of the intrinsic properties of xenon that lends itself to being a dark matter detection medium. So first of all, as I said, with thinking about the target mass, well, xenon would be pretty well matched for a 100 GeV mass WIMP. And as you can see in the top right there, here's a sort of plot of typical recall rates for thinking about 100 GeV WIMP and a typical cross-section. Well, you can see that xenon outdoes some of the other commonly used target masses, and you can really take advantage of that recall rate if you were to push down to low energy thresholds. Of course, the obvious is that it's a noble element, it's chemically inert, which means obviously it's quite easy to handle. It's obtainable commercially through a byproduct of the steel industry. And it's few long-lived radioisotopes, and those that there are actually quite interesting for science. It's easily purified, and it's dense in liquid form, which gives rise to this property that we call self-shielding. So this is illustrated in the bottom right diagram there, where you can think about backgrounds or say gamma rays impinging on our xenon target. Well, as we increase the size of the detector, of course, the gamma rays can't penetrate that far in, so we can actually find a very background-free region in the center of our detector. This is a process we call fiducialization. So speaking to the xenon time projections and chambers themselves, well, here's a kind of schematic of what actually happens. So when an interaction or particle scatters off of a nucleus, a xenon nucleus, what you end up with is both scintillation and ionization. The ionization, the charge, we drift towards the top of the detector under a drift field, extracts it into the gas layer, whereupon we have electroluminescence that then gives us a secondary light signal. So this is the prompt scintillation is the S1, and that electroluminescence, the delayed electroluminescence, is the S2. And the combination of the two signals is very, very useful. I should also say xenon has the highest light and charge yields of all noble elements. And in fact, with this setup, we have a relatively good light collection, greater than 10%. That allows us to push down to low energy thresholds on the order of a keV. And again, as was illustrated in the history of the xenon detector, these are monolithic detectors, easily scalable targets. But the combination of S1 and S2, as you can see here, for instance, you can tell from the delay time between receiving those signals, the depth of that interaction. And then we can see with the S2, which is highly concentrated on that top photomultiplier array. So we have photomultipliers at the top and the bottom detecting the light that's produced. Because it's so concentrated, one can infer the XY position. So you get excellent 3D position reconstruction on the order of millimeters. That, as I said, with the combination of the self-shielding effect, allows us to really effectively fiducialize to exclude backgrounds. So having mentioned the problem of backgrounds, I've kind of touched on gamma rays. So these are kind of arising from primordial decay change that are in every material. So you get gamma rays, you get beta decays, which obviously don't penetrate that far unless the beta emitter is actually in the xenon itself. So we've got to be wary of radioisotope contamination that can be produced in beta particles. We've got alphas from radon that actually diffuses into the xenon. And of course, we've got cosmic rays that are sort of unavoidable that induce backgrounds too. So that comes to really the main emphasis here for kind of spearheading this technology is that the backgrounds problem is really the biggest challenge for any dark matter experiment or rare event experiment. So when we're thinking about the WEMP sensitivities of current experiments, which are on the order of an event time a year, and we think about the typical particle flux for a detector on the surface, which is, 10 to the 12 times bigger, you can kind of comprehend the magnitude of that problem. So we have to think about mitigating backgrounds through kind of discriminating the backgrounds or having a way to discriminate built into the design, making sure that we build cleanly so that the materials are radio pure and controlling any contaminants when we construct. And then also, obviously, the analysis in terms of assessing what backgrounds are there and ways that we might reduce them in a given physics search. So as the cartoon illustrates, really it is a needle in a haystack kind of search, and we're trying to reduce that haystack down as much as possible. So I'm now going to transition into Lux Zeppelin. I teased it before. Well, I'm part of this collaboration, which has around 250 collaborators. So I guess you can say it's fairly small for these big science particle physics experiments, but to me, it's plenty big enough. 38 institutes spread across the US, Europe, and Australia, of which there's about 10 in the UK. And we're operating the world's largest dual-phase xenon TPC with 7 active tons. And in fact, we're the world-leading WIMP search detector, and we actually achieved that with just 6% of our planned lifetime of 60 days. So what has made us successful? Well, going underground, as I mentioned before, with cosmic rays inducing backgrounds, going underground means that we reduce that cosmic ray flux or the muon flux by a factor of 10 to the 6. In fact, we're based in the beautiful Black Hills in South Dakota at the Sanford Underground Research Facility, formerly the Homestake Mine, where Ray Davis performed his famous neutrino experiments. And we're about a mile underground, and there's a whole campus there. There's other experiments, such as the Majorana demonstrator, but we occupy the Davis Cavern in the Davis campus. And you can kind of see here, this is just an illustration of various different underground sites around the world, of which there are very few, in fact, that are working science facilities. But with SURF here, you can see that we're performing pretty well in terms of reducing that muon flux. The other aspect, as I said, building in the discrimination into the design with the time projection chamber, we mentioned that we've got both the S2 and the S1 signal. And in fact, the ratio of S2 to S1 differs between recourse that happen off of electrons, which you might expect for gamma rays and beta particles, because they're going to be better matched to the electrons in the atoms, versus the nuclear recoils that you might expect for our WIMPs. And this is really a nice illustration from actual calibration data from LZ, where we've got our electron recoil calibration. In fact, this is tritium beta decays that we injected into our detector, compared with nuclear recoil calibration, which were deuterium neutrons that were fired into LZ. But you can very see the visual separation between the two bands that these calibrations prescribe. And in fact, the metric that we kind of use is how much leakage there is below that median of that nuclear recoil band, which is actually less than 0.2%, which is, you know, a pretty stunning statistic. So as I said, also trying to minimize backgrounds that are introduced when we actually build the detector. Well, we performed some 2,000 radioassays across various sites. So this is some gamma spectroscopy data that was taken in the UK. And that helps us kind of inform which materials we'd like to build our detector with, which are relatively radio pure, to them that therefore don't introduce backgrounds for our WIMP search. We also built the detector in a radon-reduced clean room with strict cleanliness protocols. You can see someone garbed up in clean room garb there. We also, in that right image, we're performing sort of periodic checks. This is one done under ultraviolet light, looking for any dust deposition that could have happened during construction. And and dust, obviously, being like all materials, can harbor radioisotopes that we want to avoid, that can introduce backgrounds into our detector. So there were a lot of very stringent controls in place to make sure that we didn't introduce any significant contamination when building LZ. And this now is a schematic of LZ itself. So in addition to the 7-ton TPC in the middle, you can see a sort of nested structure of different detectors. In fact, surrounding it, it's kind of difficult to see, but the cryostat in which the TPC sits, well, that is also full of xenon. And we need a little bit of a standoff there because of the high electric fields of the TPC field cage and the cryostatic ground. So there's a few centimeters there. And we thought, why not instrument this? So what we have here is our liquid xenon skin detector has about a couple of tons of xenon itself, and that we can use to tag sort of gamma rays that are coming into our detector that might multiply scatter. We also have this outer detector here that's full of gadolinium-doped liquid scintillator. I'll talk a bit more about that in a minute too. But this gives you a sort of idea of how LZ's been put together. And these three nested detectors sit in a 240-ton water tank that itself then attenuates radiation coming from the cavern. Just to help you visualize all this a little bit better, here's some neat pictures from construction days. You can see that field cage. If you're able to see it with any resolution, you might be able to count the 58 field rings that go up the detector that therefore help us produce that or control the variations in our drift field. But you see all of these pictures have a large amount of white, and that is PTFE or Teflon. And that we use because it has a very high, I think it's over 95% reflectivity for xenon, very vacuum ultraviolet light in the 175 nanometer range. You can see here, and that's the bottom of, if you imagine that cryostat in which this sits. We've lined that cryostat and put some further photomultiplier tubes in to form our bottom skin. You can see the outer detector there. That's been instrumented with a Tyvek curtain, again for reflectivity. You can see the acrylic tanks and the 120 8-inch photomultiplier tubes there. And at the bottom is really that panoramic view inside the water tanker nearing completion of installing LZ. We can get a sense of the size of the detector. So that's a person there. So it's about a couple of people person's height, tall. So to describe that veto detector system a bit better, this triumvirate of detectors then. So bearing in mind, of course, WIMPs we expect to like scatter once, if at all, in the TPC. We can very well then exclude anything that scatters more than once, and therefore in our veto detectors as well. So here in that top left image, you kind of see some examples of, say, a gamma ray, which I said, you might tag in the skin. But also neutrons, and neutrons are particularly dangerous, as you might have seen earlier, because they can cause nuclear recoils that, if they're single scatter nuclear recoils, one can't really distinguish from those of a WIMP. So we have to be very mindful of those. Now, neutrons, if they traverse through the TPC, they will almost certainly end up in the outer detector. And as I said, this is gadolinium-doped linear alkyl benzene. And the gadolinium is there because it has the highest thermal neutron capture cross-section of all elements. So the neutron, in all likelihood, will capture on that gadolinium. And when things sort of de-excite, you end up with almost 8 MeV of gamma rays that are sent in all directions from that capture site. So actually, a telling feature of a neutron event is, and you can see this is going top down, TPC skin, outer detector. You can see here the neutron actually going through and scattering in all 3 detectors pretty much immediately. And then a little time afterwards, maybe tens of microseconds afterwards, the evidence of the result of that capture, where we see gamma rays being seen in both the outer detector and skin. So this is a very telltale feature of a neutron that we can use to therefore exclude neutron events. The last point of call then is trying to put all this information together and model our backgrounds. So here's our sort of CAD that's being used in our simulation framework for particle tracking. Now, we use those simulations in conjunction with information we have from radioassays and any measurements that we perform in situ in LZ, typically in sort of higher energy sidebands to the WIMP search, to produce a backgrounds model. And in fact, this is the data from our first WIMP search, where you can kind of see, well, you've got a representative WIMP contour there, but you can see also contributions from other backgrounds. We have argon-37, a cosmogenically activated radioisotope with about a 30-day half-life. That's present at the beginning of our data taking. But most of the backgrounds we see form this band, which is that akin to that electron recall band that we saw earlier. So they're mostly beta decays from contaminants inside the xenon. And we can also look at it in reconstructed energy space, where you can see some nice peaks there. But the main point of the backgrounds model really is then we have then a basis to perform statistical tests of our data and to see whether our data kind of conforms better with the background's only hypothesis, or whether it could be consistent with there being the presence of a physics or WIMP signal. So I'm now going to kind of move on to describing our latest results, and this is the timeline of getting to that point. So back just before COVID, we had brought the TPC underground. Of course, we were hindered a little bit with COVID, but we managed to complete installation towards the end of 2020. Commissioned our detector, took that first 60-day science run, which was already giving us world-leading results. And then we took our time to kind of study things better and produced a new set of data and a new WIMP search result that I'll describe now. So I'm going to just detail some highlights en route to that. So here's some particularly nice plots that kind of show us calibrating our energy response in our time projection chamber. We can neatly see some peaks here. We've got basically electron capture and gamma ray contributions from xenon 127, iodine 125. We've also got xenon 131M, which is another beta K plus. So it's another gamma ray contribution there. But what we can plot out from this is what's known in the field as a Dopé plot, which neatly shows then the anti-correlation. So bear in mind with electron recoils, there's very little given off to heat, so you're just trading off between light and charge. So you can see here with that trend, that inverse correlation between light and charge for these various different points that we can extract off of our data. So that's pretty neat. And in fact, then allows us to kind of define an energy scale for our reconstructed energy. So we can analyze the backgrounds, as I said, adjacent to our WIMP region of interest so that we're not biasing ourselves. And we perform fits in the energy space, trying to anchor those key gamma ray lines that we have from those primordial decay chains. And you can see quite how many different components there are in this fit. And this was quite an achievement, ranging all the way, we grayed out that region of interest, all the way up to 2.6 MeV or so, which is the thallium-208 line, which is the last real line that's naturally produced from our radioisotopes. So with that, we actually have the basis for looking for other types of physics as well in this range, should we wish to, but it's quite a feat that we managed to fit all these components out. Another key background is radon, which, as I kind of inferred or insinuated before, kind of can leak in and emanate into our detector, since it's also a noble element and has a high affinity to do so. And what we have here, very small diagram, I know. So from radon 222, if you keep going down, you'll end up with a beta decay from lead-214. And lead-214 can be dangerous because if you had a gamma associated with that beta decay, well, you could get a beta scatter and a gamma ray scatter, which immediately rules it out as a single scatter and therefore not a WIMP. But about 12% of the time, you can get a gamma-less decay, so just the beta decay, which can then permeate the WIMP region of interest and give you a single scatter. So we really care about this. This is actually our biggest background for a WIMP search. And we discover something really neat. So, the first bit of this stage is just 3.1 minutes half-life of the polonium-218. So in fact, we can correlate a radon-222 decay with a polonium-218 decay. And that's kind of neat because we can actually map out the flow of the xenon in the detector. So in the left there, you can see some flow vectors that we've been able to define when our detector was in a sort of low mixing circulation state. And you can see how homogeneous that flow is. And in fact, we could identify a relatively radon-poor region in the bottom middle of our detector, which is useful. So we thought, why not take that process further and see if we can infer where that lead-214 is. Now, lead-214 has a bit of a longer half-life of almost 27 minutes, but we can kind of define these sort of streamlines where we would think probabilistically there might be a lead-214 there and exclude them, or in fact, we used them in our analysis, but said that they would be lead-214 heavy. So we've devised this first pass at this. A paper is incoming, and we've been able to tag 60% of that lead-214 in just 15% of the analysis volume. Now, another neat thing that we've noticed is looking at electron captures more carefully. Now, we can get instances where, you've got, for xenon at least, a 5.2 keV L-shell electron capture. That would be in our WIMP region of interest. Now, it would have a gamma associated with it, but sometimes that gamma ray is not detected in the skin or somehow escapes detection entirely. Now, one neat thing that we've seen, I was referring to there being no long-lived radioisotopes that are problems for us. Well, some of these harbor new physics in themselves. So, in fact, our competitor experiment, Xenon-1 was able to measure or observe Xenon-124 neutrino double electron capture for the first time, and that's been branded the world's rarest decay. It was a Nature paper. And that half-life is over 1 trillion times the age of the universe. So that's really, yeah, quite an interesting statistic. And we've actually measured that in LZ as well. And with these electron captures, compared to a beta decay, because you end up typically with an Auger cascade or some X-rays, the pattern of deposition of those of that cascade, energy deposition of that cascade, tends to be more nucleated than that of a beta decay of the same energy. So it appears actually a bit more dense and more nuclear recall-like. So we've noted that effect and inferred actually that the effect would be greater in the double electron capture case for an LL shell double electron capture. And that we've seen for the first time in an LZ analysis. So I'll refer to that in a bit. Last thing I wanted to point out is the concept of bias mitigation. So we didn't blind our data. In fact, we did this process called sorting. So sorting involved producing fake signal events. So we stitched together S1s and S2s from sequestered calibration data to try and mimic actual nuclear recalls that we might expect from our WIMPs. So to do so, we kind of looked at the parent, drew from a parent distribution, which is an exponential WIMP recall spectrum, as you saw for the Xenon that I showed earlier, and plus added a flat pedestal to make sure things were filled out. Capping the rate then with the limit on the WIMP interaction cross-section that we found from our first science run. And of course, not exposing any of the parameters of the salt until after we've finalized our analysis. So as obviously not to bias how we approach things. So lastly then, for the latest WIMP search data, just a little bit of information about the cuts. I won't go through it all in gory detail, but here on the left, you see the signal efficiency that we have for nuclear recall. So we're looking at roughly about 5 to 55 keV nuclear recall, where we're above the 50% efficiency. So that's perfect for looking for, around 10 GeV WIMPs all the way up to tens of TeV WIMPs. So not only do we have a region of interest, which is defined in terms of our observable S2 and S1 and S2, we have the Vita anticoincidence cuts that I mentioned before, and then some S1 and S2 cuts, space cuts, to kind of target anything with an odd shape that could be pathological and not actually an S1 or S2. But we also have the fiducial volume. I mentioned fiducialization. This is the result of that on the right here, where we're avoiding all these backgrounds that lie towards the wall or the edge of the TPC, which is actually curved in this space because we've not corrected radially. This is actually what you would see or infer just based on the curvature of the drift field. And in fact, there's places that were slightly hotter. So the two lines, they kind of represent the least and maximal extent that we cut in radially to try and avoid these small backgrounds. You can also see the effect of the vetoes. Unfortunately, I haven't been able to erase the sidebars here, but in red, you see the events that are prompt tagged, mainly in the skin. So these are kind of gamma rays that are leaking into that top corner there through the gas layer where they're not really that stopped, as well as tagged by the outer detector with this delay tag that I mentioned before to try and capture potential neutrons, but they also just capture things where there's accidental coincidences in the outer detector. But the fiducial volume is pretty successful at, therefore, mitigating these surface backgrounds and whilst preserving then 80%, roughly 80% of the total mass for analysis. So here are these data. In fact, I'm going to see if I can kind of shut this okay, because it's annoying me a lot, but I can't see my mouse. Okay, right. Sorry about that. Okay, right. So here are data from WIMP Search 2024 that's been taken between March 23 to March 24, roughly 220 live days with the 5.5 tons of the fiducial volume, so 3.3 ton years worth of data. And you can see these, I think it's 1,227 data points. And in red here are the salt that we actually put in, which of course we didn't know at the time, but this is what we found when we did the unsalting process. You can see pretty much all of them kind of lie in this representative WIMP contour here. And you can see the 1 point all the way to the right, which would be for, yeah, something a much higher mass. You can also see, I didn't explain the concept of accidental, so I ignored that, but you can also see the xenon 124 there, which, as I said, is kind of pulled down from that electron recall band towards the nuclear recall band. So the 7 salt events disappear when we unsalt, of course. And then we have the 1,220 events remaining for analysis. And what we did was combine this set of data with the 60 days that we had before for WIMP Search 2022, giving us a total of 4.2 ton years worth of data to look at. And just to kind of highlight the effect of the radon tag, which we did actually use to give us different exposures that we combined in this analysis. But here, visually speaking, it kind of helps us to disentangle the different background contributions. So if you see on the left there where things are radon tagged, well, you see comparatively little leakage of anything below that electron recall band, even though it's a much smaller exposure. Compared to the right here, where you can very clearly see things that are probably xenon 124 populating those xenon 124 contours. Of course, then building up the backgrounds model, and this is what we expected to see. So we're dominated by electron recalls, as you could actually see with the data, expecting 1,207, mindful that we had 1,220 events left, most of which we think are going to be lead-214, comprising more than half of those backgrounds. We have various other contributions as well from the 2 neutrino double beta decay of xenon 136, for instance, and solar neutrino electron recoils, which are irreducible backgrounds. And on the right there, you see, if we looked at that radon tag exposure, quite how much of that lead-214 is being sucked out into that exposure. The nuclear recall counts, as we would hope and want to achieve, are low and are dominated by the prediction of the boronate solar neutrino coherent elastic neutrino nuclear scattering, or SEVNS process. And this is just, it's too much detail here, but it's sort of trying to illustrate what our expectation was and what we were able to fit out, where you can see most of the numbers don't change that drastically and lie within sort of the expectations. The good or bad thing is that the best fit of zero WIMPs was found at all masses that we tested, and good agreement was found with the background only hypothesis in all the spaces that we looked at, including reconstructed energy there. So unfortunately, we didn't find WIMPs, but what we did do is set yet better results looking at, say here, the spin-independent WIMP nucleon interactions. So we peaked down to a best limit of a cross-section of 2.1 times 10 to the minus 48 centimeters squared for a mass of 36 GeV. And we actually surpassed our previous results with those 60 days of that first one by around a factor of 4 or 5 at all masses that we see on this plot. So as I said, this is just looking at the WIMP cross-section now against the WIMP mass. And that's sort of the characteristic shape that one would expect to see. So the results of the analysis on arXiv soon to be on PRL. And we also looked at the spin-dependent case as well, where we have sensitivity via the isotopes of xenon 129 and xenon 131, which have an unpaired neutron. So in addition to WIMPs, I'm just going to say that we can do a myriad of other different physics with LZ. So with the electron recall events that we have, we can actually look for various neutrino properties, solar axions, axion-like particles, for instance. So here's an example from a paper we put out relatively recently, where we've set limits on the neutrino magnetic moment and effective Miller charge. We can also look for various other dark matter candidates and at much higher energies as well. So here's an illustration of one of these searches where we were looking for ultra heavy dark matter, or MIMPs. So this was really to illustrate that these detectors are broadband. They can search for a wide range of different candidates, different types of physics at various masses and energies. And why that's important? Well, what is actually next for LZ? Of course, we will continue to run, and we're leading the field. So there's genuine potential for discovering WIMPs still as we probe uncharted electroweak parameter space. And we are set to run through to 2028 currently. We also want to keep demonstrating that we're a multi-physics machine. So on one part, we can look for neutrinos double beta decay of xenon 136. And that's compelling because that would kind of hint then that the neutrino is its own antiparticle, or it's a Majorana particle, and then give us sort of an indication as to the sort of matter-antimatter asymmetry that has arisen in our universe. Now, of course, I've illustrated that process with those Feynman diagrams at the top, but on the bottom left is the reach that we might expect, which is comparable to some of the sort of dedicated experiments in the field that are looking for neutrinos double beta decay. We also hope to look for sevens with wild or astrophysical neutrinos, which would be the first discovery, if you can say it's a discovery, of that process with neutrinos, and not reactor neutrinos that Cohen used to demonstrate that this process exists. So here's where those sevens events might lie in our S2, S1 observable space. And all of this is important because we might think further into the future with an even bigger detector. And that bigger detector has a wide range of accessible physics, all sorts of neutrino physics, be it studying atmospheric, solar, or even supernova neutrinos. As I said, both double electron capture and neutrinoless double beta decay, which, here we could really be world leaders in that department. And just to give you an illustration of what's kind of being planned, we have LZ here with the person next to it. And then we go forward towards XLZD. So it will be roughly an order of magnitude bigger than current experiments, using a 60 to 80 ton active mass TPC. Now, LZ is part of this equation. That's the LZ and XLZD, but we've joined forces now with the other foremost experiments in this field, which are Xenon, aptly named, and Darwin. So those are the X and the D in XLZD. And now we constitute roughly 500 people, and that number continues to grow with 72 institutions, 17 countries. So the point of this machine is that it's not only the definitive WIMP search experiment, but it is also going to be a rare event observatory, allowing us access to all sorts of different physics. Now, one place where this could be is at Bowlby. So I'm not sure how many people are familiar with the Bowlby Underground Laboratory. Well, this is a salt mine that's located in, or still an active salt mine, I should say, that's located in the northeast of England, in North Yorkshire, on the coast there, near Saltburn and Whitby. Now, it's the UK's deep underground facility. It's one of 5 in Europe, less than 15 globally. So as I said, these facilities are pretty rare. It's operated by STFC, partnering with the mine operator. And yeah, there's a lot of things going on there at the moment, some astrobiology, some muon tomography. It's not just low background particle physics, but it does have a long history of dark matter. The Zeppelin experiment I mentioned before, DRIFT, MUSE-G, which is a spherical proportional chamber. And it also hosts BUGS, which is the Bowlby Underground Screening Suite, that has world-class material assay facilities, high-purity germanium detectors, XIA alpha detectors, and radon emanation too. Yeah, so this kind of shows one of those detectors at BUGS. The Zeppelin 3 detector that was once there, that's now in the Whitby Science Museum. Whitby Museum, maybe not Science Museum. And that's a kind of illustration there of the current facilities that exist at Bolby. So, can we imagine XLZD coming to the UK at Bolby? Well, there's a proposal to host XLZD, building a bespoke new facility at Bolby. So this would have two new parts to it. Stage one is at a 1,100 litre depth. And that'll be where kind of many aspects of XLZD will be staged. So building up the cryostat and other components for it to then be transferred to a later stage, the stage 2 facility that will be at an even lower depth where the thing will be installed and operated. So there's quite a high commitment from SCFC to see through this Bolby development project. But the great thing about this compared to other potential sites for XLZD is it would, because things are already in motion, facilitate an aggressive schedule. We could be even starting by 2032, 2033. It would facilitate a larger experiment of up to 80 tons of active mass. And as I said, it will be a purpose-designed laboratory, so we could actually think about our needs in terms of, say, radon reducing the region that we're operating in, making sure that we have all the various facilities that we need for cleaning, etc. So there's excellent strategic alignment there with the, well, there was the whole thing of levelling up the north of England, which I guess is not quite called that anymore, but there's still an incentive to bring more jobs and investment to that region of the UK. And so it really aligns with the goals of the UKRI, SCFC, and the UK government. So pre-construction is actually underway here. We've just actually received a grant to start working on things, R&D towards this experiment, which involves around 100 physicists in the UK, physicists and engineers at 14 institutions. Now, there's a lot of challenges here that we need to think about. First of all, the detector is going to be so big that actually getting it down into the mine is going to be a bit of a challenge. So we have to think about how we might weld a cryostat underground and do that cleanly. Things like this. Thinking about radon, this picture here is actually an illustration of us trying to electroplate some metal surfaces to then prevent radon from even emanating from them. So there's a lot of thought going into this. And as I said, in parallel to that, a lot of progress going on at Bolby. So we've actually, this is just a few weeks ago now, the excavations for stage 1 are almost complete. So as I said, the main purpose here is to try and bring this project to Bolby. If it doesn't get chosen to be at Bolby, there will be a significant UK contribution wherever XLZD is. So that was really my last slide. I hope I've shown you that, well, detecting WIMPs or dark matter is really challenging. We need to think about target mass, background rates in particular, and a low energy threshold. And xenon has been the ideal medium thus far. And we've seen with LZ that our history of putting together this experiment, thinking about its design and its construction and the backgrounds from the very beginning have enabled us to reach these world-leading limits. And there's really, and I want to emphasize this in the room, a really exciting opportunity for the UK to host XLZD. I mean, if it comes to the UK, a lot of particle physics will be moving into this experiment. It's a next generation experiment, not just from WIMP dark matter, but other dark matter, other rare processes and beyond the standard model physics. So it will really be an observatory that we could study a lot of things in. And that's my last slide. So thank you very much for listening. Thank you. Thank you very much for the talk. So we have a few minutes for Q&A. Does anyone in the audience have any questions?
You mentioned that other physical goals and LZ, like searching for dark-matter decays, material dark-matter decays. Like these events are typically high energy events, being the liquid xenon TPC. And how do you deal with like potential saturations for PMT since LZ doesn't have any down readout system?
That's a very good question. So in fact, we have dual readout of our photomorphic tubes. We read them out in low gain and high gain, effectively a factor of 10 between them. So obviously the high gain is very useful for the low energy stuff, like the links. Low gain, in almost all cases, right, up to the end of scale that we care about for double beta decay, things don't saturate. So we're actually pretty good there. But regardless, there have been loads of studies as to, well, you've got PMT saturation itself, but you've got ABC, so I was referring to ABC saturation. Yeah, to kind of reconstruct the pulses and figure out what the actual S2 signs would have been from the pulse shapes. Questions?
Do you have any theoretical limits on how low the width the nucleus interaction cross-section can be?
Yeah, so in principle, we can keep going back. So a lot of the natural models, we're really impinging on sort of the models that have Higgs-mediated interactions now. So sort of the so what's the word? The tree level, the base level interactions have sort of been excluded. We're now looking at sort of Higgs portal sort of models, extensions to minimal supersymmetric models, but there's still a lot of viability going down. Now, the big problem for us, and why I've referred to this as the definitive WIMP experiment, is that we begin to now see more sevens from atmospheric neutrinos and solar neutrinos. That makes it kind of difficult to start delving into that fog to distinguish between a WIMP. So there's still a lot of parameter space there that we can do with XLZD. Certainly that experiment will probably see out my career, you know, I'm relatively young. Yeah, I mean, it will run for probably 2 decades when it does come online. So I'm not particularly worried, but yes, there needs to be more thinking as to which other areas that we want to look in. So coming back to that plot, right, I mean, so exposure would take us further down, so just building a bigger thing. We can also look towards the left as well by trying to further lower threshold. So we're looking at things like S2 only searches where the S2 gives us, it's a proportional scintillation signal, so we get a lot of light, which means we're actually sensitive to much smaller recalls and thus lower masses that we can look at. So obviously you lose some of the discrimination ability, but that's the kind of thing we've been looking at to try and look for lower mass candidates as well with Xenon TPC.
I have a question
Sure.
tangent to that.
Yeah.
So I guess this probably sets a very stringent limit on what sort of WIMPs are out there, and which models are like correct and incorrect, etc.
Yeah.
Like, yeah, what does your the result kind of like, does it have a huge impact on how people look at this?
Yeah, as I said, so I mean, it would be nice to just put some. I don't have the plot to hand, unfortunately, but you can look back at there's various strategy processes. One of them is SNOMAS in the US, where a nice plot was produced actually that kind of showed the sort of loci of various different models, the Higgs portal models that I was kind of referring to. So these are still very much viable areas to be looking at.
So you mentioned sort of neutrino limits.
Yeah.
So I actually live very near to Mulvey, and scientists there give talks about it. Talks I asked about this. So they said one of the potential experiments was finding the sort of direction of neutrinos or the dark matter detections of the neutron. And so you can exclude certain events. But are there other ways to exclude these neutrinos, or is it really just relegated to finding out where it comes from?
So directionality is a big thing which we can't do in LZ, but you can do in so I mentioned drift, I think was one of the ones that was in Volby, which is a wire chamber. in theory, you could build a really big detector, and eventually there are spectral differences in the Riemann spectrum. You could begin to try and expose those, but it would be you need to get to a regime where you've got the Poisson statistics of your sevens and what that that well enough. Maybe it's constrained from other measurements from I don't know. Well, for instance, the boron 8 that we've just seen is well constrained from SNO in terms of the boron 8 solar neutrino flux rate. So we'd be reliant on other experiments to kind of feed us information to kind of really constrain the sevens rates of these other neutrino flavors, and then we'd have to then hope that we could see the excess above that. But it does get pretty challenging, and I think that's why I say it's the definitive experiment. It would be very difficult to put forward a case to build an even bigger one, given those challenges, unless there's new innovation in the field.
I was just thinking, like, in this plot, the data starts from 9 GeV.
Yeah.
And like other collaborations like Xana and Panax, they have looked at like between 6 and 8 GeVs, the boron 8 solar neutrino range.
Yeah.
I was just curious about did LV like look at the data in that range, and what's the
right? So the 9 GeV was just capped by the fact that we kind of conservatively set our threshold, right? So I mean, there's a whole lot of
that's the optimal sensitivity range.
Right, exactly. As I was just saying, we could try and do things to lower thresholds, and that is kind of work in progress at the moment with our analysis. So I mentioned S2-only searches. Another thing that we're looking into is lowering the coincidence requirement on the PMTs, photomultiply tubes, for our S1 signal. These are ways that we can extend our region of interest for WIMPs and then push towards the smaller, sub 9 GeV massive. So that is in action right now, but given how well they're doing here, we didn't see the need to push down yet. But it's in the pipeline.
So yeah, if you have any more questions, feel free to come down and ask Amy about it. We'll stay here for a few more minutes, and thank you all very much for being here today. Hope you have a nice rest of the week.
Thanks.
It's good.
There was a question in chat. You have a moment
Oh,
here. It's fairly relevant.
What was the about?
oh. Okay.
I just want to be nice to them because the stream kind of didn't go very long. Oh, I think they hear you.
Oh, I just need to speak. Sorry.
Yeah.
Yeah. So the main background level we care about is, well, we've seen the muons, right? Where if I bring that slide back up, you'd be able to see where the Bowlby site is now, and probably infer then how much better the muon flux will be when we're at the 1300 meter site. So there's that aspect that I think we're on a par, at least with surf, if not better. And then there's the radon, where the salt, the structure of the cavern means that actually there's intrinsically less radon that's coming out of the rock than most other sites. So I can't remember off the top of my head. I think it was like 3 microbecquerels. No, actually, I don't know. No, 3 becquerels per cubic meter or something like that. But it's much lower than the most other sites, so we can really take advantage of that when we're thinking about constructing underground and avoiding plate out of radon installs. Hope that helps.
Thank you.
No worries. I have no idea if I'm speaking into the void or if there's someone there. But will I switch this off?
Thank you.